explained so far are the basic equations of fluid mechanics. One is the continuity equation, which is based on the principle of conservation of mass. The next is the equation of motion. Which is based on the balance of momentum. Can you please open the door? Balance of momentum can be written. We're moving now to spatial coordinates. Everything I'm writing in terms of that. Basically, there's one equation here. There are three equations here. This is a vector equation. For each component of the momentum, I'll get an equation. Right? So there are three equations here. And one, so the variables are rho. Of course, it's a function of time as well as position in general. 4 variables, 4 equations. In principle, you should be able to solve the equation. Right? So, however, there is still data that must be provided. I need to know what this is, the body force, and I also need to know how to determine this. So they are as of now unknown. Right? Now the body force is an external force. Right? So it will be external to the fluid. I mean, it's not going to be related to the properties of the fluid. And for all practical purposes in this course, V will simply be equal to G, right? Which is, or I can rather put this as the magnitude, simply be G, the acceleration due to gravity. So that's the only external force we are going to consider in this course. Right? So external forces will not be given too much importance in this, especially basic continuous mechanics. The fundamental quantity that characterizes the contact force will be the one that will be of primary importance, at least in this course. So now the stress is an internal force, right? It's a contact force. So clearly it cannot be just specified without any reference to the motion of the fluid just like that. Right? So obviously it has to be related to the density and velocity in some manner. Right? So once it becomes determined as a function of the primary variables that I have to determine, then there is no problem. I can go ahead and look at the solution of the problem. Of course, I have to provide boundary conditions and initial conditions and so on. That comes later. First thing is specification of V. So V is the body force. We are not going to spend too much time on it. The contact force is what we will now look at. How it is to be related to the properties of the motion. So we will take up now the work of Stokes and three important hypotheses of Stokes will lead to a determination of T in terms of the properties connected with the motion. So I'll list out three of them. One is T, the stress tensor. It's a continuous function of the so-called deformation tensor. I haven't defined it yet. D. There's now a new tensor that I'm introducing, the deformation tensor D, and mathematically can be expressed as is effectively determined when D is specified. That's what it means. There are no other variables explicitly determining the stress. And of course, we have seen earlier, this is not to be confused. This doesn't mean the stress tensor doesn't depend on position and time. Those are the basic variables of motion. But here what we are saying is that the stress is related to the deformation tensor. What is the deformation tensor? I will define. And the second one is often referred to as the principle of isotropy. When Aris calls this the fluid is isotropic. Both Aris and Selin also say there is no preferred direction. In space, we see what these words mean shortly. Then the third is T is equal to minus Pi when D is equal to 0. This is somewhat easy to understand. What this says is that when there is no deformation, then effectively whatever model you are proposing for the stress tensor, it should reduce to one corresponding to the hydrostatic stress, which is what is given by minus P times the unit tensor. I is actually the unit matrix. We call it the unit tensor. Simply 1 0 0 0 1 0 0 0 1. When there is no deformation in the fluid, then the state of the stress should correspond to that of when it is in rest. Right? That is the hydrostatic stress, and it will have this form. Now, based on these three hypotheses, it is possible to show 1, 2, and 3 means that T actually can be expressed in the following way: alpha plus beta E plus gamma square. Possible to prove the shear stress must have this form: alpha times the unit tensor, beta times the deformation tensor, plus some gamma times the deformation tensor square. For all practical purposes, you know how to multiply a matrix by itself. So D squared simply means B multiplied by itself. What about the alpha, beta, and gamma? They need not necessarily be constants. They are actually functions. They are scalar functions of the invariance of D. So I introduced many terms that might not make any sense to many of you. Right? One is, what is the deformation tensor? We haven't defined it. What do you mean by isotropy of? What does this mean? And the third one, what do we mean by invariance? And of course, the final thing is this amazing result. Why should we even have this form based on these three assumptions? Right? Those are the points that we would take up one after another. First, the definition of the deformation tensor and why it is called as a deformation tensor. We see. So, to that, first to discuss what is deformation. What do we mean by deformation in a fluid? So for that, D is related to the velocity gradient tensor, which we have already introduced, right? So we know what the velocity gradient tensor is. We have defined it so that this is dvj by dxi, the ij element. The velocity gradient tensor we have already defined, right? So it's very easy for you to write down what this is going to be, right? So you want to write it down fully. This will be dv1 by dx1, right? dv2 by dx1, dv3 by dx1, and so on. That's a matrix, velocity gradient tensor, which we are calling. Now, every matrix, the fundamental theorem that every square matrix, this is now not restricted to just 3 by 3 matrix, every square matrix can be split as the sum of a symmetric matrix associated with A plus an A. This decomposition is fundamental. Any square matrix, not just 3 by 3. Here we are dealing with a 3 by 3 matrix, so it applies to this case as well. Plus, it's very easy to show that the following form satisfies this rule. So this would be half A plus A transpose plus half A minus A transpose. The symmetric matrix, all of us know what it is, right? Symmetric matrix means that means A is symmetric. The symmetric part is equal to Ji. That's the symmetric part. What of the anti-symmetric? Minus. So A anti-symmetric is defined minus A anti-symmetric Ji. Right? So it's very easy to see that the two of them together add up to A. That is very easy to see. I have half A, another half A, so it adds up to A. This is half A transpose minus half A transpose. It also adds up to 0 actually. So the net result is A. It might just be a little bit less obvious to see that this is symmetric and this is anti-symmetric. That I'll get you to prove that by just writing it out what transpose is and then adding the two and then taking half of it, you can easily show that this will be symmetric and this will be anti-symmetric. Now a crucial property of any anti-symmetric matrix, can you give one striking? Diagonal elements must be 0 because Aij equal to minus Aj I. So if I put J equal to I, here no summation implied, and I put J equal to I. Then it means so for J equal to I get Aii anti-symmetric is equal to minus Aii anti-symmetric. No sum over I. It refers to the ith element, the diagonal element corresponding to the ith row. Clearly then Aii anti-symmetric is 0. So the diagonal elements are 0. So if you look at this, now any symmetric matrix, let's now focus on 3 by 3 matrices. Right? 3 by 3 matrix has 9 independent elements. You can easily verify that the symmetric part, any symmetric matrix has only 6 independent elements. The diagonal elements plus 3 of the off diagonal. Right? For instance, A11, A22 and A33 for the symmetric, if A is symmetric. Plus A12, A23 and A31. I can include any one of the other 3. Because A21 is equal to A12, A32 is equal to A23, A13 equal to A31. So I have only 6 independent elements that I have to specify. Anti-symmetric, I know the diagonal elements have to be 0. Of the other 6 elements, they are all related by this. The off diagonal elements, so A12 for the anti-symmetric would be equal to minus A21 if A is anti-symmetric. There are only 3 independent elements. So there is a match. 9 is split into 6 plus 3 independent elements. So there is totally still 9 independent elements. That's preserved. So now, in the same way, now I can split the velocity gradient tensor into a symmetric and anti-symmetric part. The symmetric part is what is called as the deformation tensor. The anti-symmetric part is, we will call it as the tensor represented by omega. The symmetric part of the velocity gradient tensor is what is denoted by D and is referred to as the tensor. Now I can write the general formula from this. So the ijth element would be half A, the ijth element of A. So this would be Ej, comma I plus Ei, comma J. Right? So I'll let you write out what it will be in matrix form, what would be D look like, and omega what it would look like. Right? You can write it down explicitly, but this is the general formula for the ijth element. The omega ij is clearly given by half times Ej, comma I minus Ei, comma J. You have to understand the ijth element, the way we have defined it, the velocity gradient tensor is actually given by Bj, comma I, not Bi, comma J. When I take a transpose of that, then I will get Bi, comma J. Are there any questions about the notation and how we arrived at this? Now, why is D called the deformation tensor? That's what we will look at next. For that, we have to understand what we mean by deformation in general in a fluid. Because for a solid, let's say I have a rubber band, if I stretch it, you can easily see it deform. If I have a balloon and I compress it, I can easily see the deformation. When a fluid is flowing through a pipe, whether it be liquid or gas, we don't really see that it's actually deformed. Clearly, there is some deformation taking place, right? When there is a flow, that we will see how it is. We may not be able to see it as manifest as in the case of a solid, but deformation is still there, so we need measures of deformation. So for that, let's consider a body. Now consider 2 points. One which has a material coordinate given by psi, another close to it which has the material coordinate psi plus d psi. With respect to a fixed coordinate system, I can locate this. This has this coordinate psi plus d psi. So clearly this vector is what is called as d psi. That's the vector. Right? I'm not really worried about that. So I'll just erase that arrow. Now, this is the reference configuration. Now at time t, let us say this point has moved to a position x. Right? And this has moved to a position which I will now call x plus dx. Clearly this is what would represent the vector dx. That's what I mean by dx. So now, how is dx related to d psi? That is a measure of deformation because 2 points are a certain distance apart and are represented by the vector d psi. What happens to the relative distance or the relative vector between the same 2 points at some other instant? Right? So now I can write dx, the vector is given by dx1, dx2 and dx3, written as a column vector. And I can write from an arbitrary component of a vector dx in terms of the material coordinates. Clearly, because of the transformation xi equal to I can write this as with respect to the change in psi. Right? It can be written like this: dxi by d psi. But of course, time is why I am not writing the time also is not coming in. But we we are only talking about how dxi is related to d psi, right? I can certainly write it like this. And this is sum over j is implied here. It's a function of the psi 1, psi 2 and psi 3. This is how it would look like. Now this is clearly the ijth element of the matrix J which we have introduced earlier. Said that the J is invertible actually. There is a one-to-one transformation between x and psi. We've looked at some of the properties connected with the Jacobian of the transformation J. So I can now compactly write this as dx is equal to J times d psi. In the matrix form, because this is dxi. So I were to multiply a matrix with a vector, this is exactly what I would get jij d psi j, sum over j equal to 1 to 3. Here the repeated index summation convention is an operation. So I don't have to write the sum, it's implied here. This is what I would get. So the j itself represents some measure of deformation. It tells how 2 points which are separated by d psi at the reference configuration, right, how they will be positioned at some other time. So this is what we mean by deformation. So the fluid has got deformed. It's looking at it from the point of view of the relative orientation and distance of two material points and how they get changed with time. But in fluid mechanics, it is not just the deformation that is important, but the rate of deformation that is of fundamental importance, as we will see. Now I am talking about d by dt of dxi. It's the rate of time rate of change of the variable dxi. So I simply differentiate this, and this clearly can be written as these are not changing with time, so I don't have to differentiate it. In fact, the whole procedure is somewhat formal, but I will just emphasize some of the tricky technical points and then see if you can at least formally understand the procedure. The final result is more important. So now I have d by dt of dxi by d psi j times d psi j, right? So now I can interchange the order of differentiation. I have already done this once, because d by dt, capital d by dt is nothing but the partial derivative of d with respect to time, keeping the variable psi 1, psi 2 and psi 3 fixed. So I have partial derivative with respect to time, and I have one of the signs being differentiated. So I can interchange the order of differentiation. So I get d by d psi j of acting on d by dt of xi, which is nothing but the ith component of the velocity. So I get this as dvi by d psi j times d psi j. Now I want to go back to the spatial coordinates. So I will do the same trick that I did earlier. So what I have is d by dt of dxi is equal to dvi by d psi j. D psi j. I've just transferred that result here. Now I will write this as dvi by dxl and dxl by d psi j times d psi j. Which can then be written as dvi by dxl and dxl, which can then be written as dxl and dvi by dxl, which can be written as dxl this of the velocity gradient tensor dv I by Li. What is this the ith component of dxl, the Li element of the velocity gradient tensor summed over L. So it's clearly the ith element of some product that we have encountered before. It's a product of a vector with a tensor. Clearly it is equal to dx dotted with velocity gradient tensor. Now it is somewhat important result. Can be written compactly in this way. Now, if I were to calculate d by dt of ds square, as it is called, the arc length square, the ds square is defined as dx dotted with itself. So what this represents is the time rate of change. I'm sorry. That's the ith component. So I've taken the time rate of change of dxi, that's the ith component of dx, is given by the ith component of dx dotted with the velocity gradient tensor. So I can write the vector expression as d by dt of dx is equal to the vector dx dotted with the velocity gradient tensor. Okay. Then I look at what would this be? This would be the time rate of change of the square of the length between the 2 points. That's exactly what dx, this is the vector dx. You see that a dotted with a is simply the square of the length of the vector a. So dx, the vector dotted with dx, would simply be the square of this length, which is referred as ds square. Now that is calculated in this way, because that is the meaning, the dot product with itself. Now I will use the product rule of differentiation for dot product and write this as d by dt of dx dotted with dx plus dx dotted with d by dt of dx. Right? The two are equal to each other because it's just a scalar dot product. I can either write it as 2 times d by dt dx dot dx or 2 times dx dotted with d by dt of dx. So that is what I will do. What we are going to write down is a more important formula than this, but it is derived from this. d by dt of dx is dx dot the velocity gradient tensor. So d by dt of ds square can be written compactly as 2 times dx. I didn't want to write it that way. Certainly it can be written that way also, and because both of these terms are equal to each other. So I can write this as 2 times any one of those 2 terms. dx. Right? So 2 times d by dt of dx is simply dx dot, and then I have dx. So this is an important result. We proved it through a series of manipulations which by now should be familiar having problems understanding any one of those steps. We'll come back to it later because I want to get to the main result of this section of the course. Now what I am going to calculate, since we have seen that the velocity gradient tensor can be split into its symmetric and anti-symmetric part, I am going to calculate what is the result we get by simply taking. So for one thing, I can write this as is equal to, we got that, which is equal to d plus omega, right? Just substituting for the velocity gradient tensor in terms of its decomposition to its symmetric part plus the anti-symmetric part. Clearly, it is easy to show that this would have in turn two parts. I can evaluate them separately. I am going to evaluate the second part first. So we get dx dotted with omega dotted with dx can be written as, well, let me calculate this. So this is the dot product of a vector with another vector. It's a very straightforward scalar dot product. But this vector is obtained by taking the dot product of a vector with a tensor. So I have to take the ith component of this, multiplied by each other, and take the sum from I equal to 1 to 3. Right? So I have dx, the ith component of this is dxj omega ji. The ith component of dx is dxi. The sum over I is automatically implied. Of course, this is sum over j also here. Right? So sum over both j and I is implied. I don't have to write that explicitly. This is what I get. So now this is equal to dxj. This is a half. We have already seen that omega ij is half times bj comma I minus bi comma j. And I can even write 2 times this so that I can get rid of the half. Right? So that 2 will cancel with this half, and I will now write this as bj comma I minus bi comma j dxi. This is equal to dxj bj comma I dxi minus dxj bi comma j dxi. What? Huh? This is dbi by dxj, this is dbi by dxj, this is dbj by dx. Two are different. Huh? No, that is that they are not equal to each other because the velocity gradient tensor is by no means symmetric. You have to understand. Of course, if your answer is correct, this is equal to 0, but not because bi comma j is equal to bj comma I. So if I want to bring it to this form, I can, this is sum over I and j, so I can interchange I and j throughout. The value will not change. So the first term I can write this dxi, interchange I and j, bi comma j dxi, dxj, sorry, minus, I write this as it is, dxj. Clearly the two are equal. Right? All I have is, here I have dxj and here I have dxj. So here I have dxj and there I have dxi. It's just a multiplication of scalars, so that two terms are entirely equal. So the net result is 0. So clearly then d by dt of ds square can simply be written as 2. Now what this says is that if you consider the effect of the anti-symmetric part alone of the velocity gradient tensor, suppose let us say t is equal to 0. Let's consider the possibility. And so the entire effect of the deformation, which is the time rate of change of the length of the element dx, right, is square of the length rather, is given by omega, and that also becomes 0. So what does it say about omega? The effect of omega effectively corresponds to rigid body rotation. What do we mean by rigid body motion? So rigid body can move in space, it can translate, it can rotate about an axis. So motion is possible for the rigid body, but the relative distance between two elements within the rigid body remains the same, whatever motion may be allowed for the rigid body. Right? So the rigid body is like this. If it rotates, let's say, about some axis, let's say two elements, before it starts rotating on here, now the distance between the two remains the same as the body moves. Either it can move, translate, or it can rotate. Right? So what this means is that the effect of omega, the anti-symmetric part of the velocity gradient tensor, is one of pure rigid body rotation. So there is really no deformation in that sense. The sense we are talking about, the relative motion is what we are considering. The relative distance, or the relative, either the absolute value of the distance or the distance vector, that is what these quantities represent. d by dt. The rate, that doesn't change. That means it effectively corresponds to rigid body rotation. So the entire effect of deformation is contained in only the symmetric part of the velocity gradient tensor. That is really causing the true deformation in a fluid. Right? Because the effect of omega is 0. So which is why Stokes saw the stress has to depend only on the deformation part of the velocity gradient tensor and not on the entire velocity gradient tensor. And he proposed that T has to be determined effectively. So he related the stress to deformation. Now the velocity gradient tensor is also a measure of deformation. After all, that is what we have first. But it was Stokes' insight to see that the anti-symmetric part actually corresponds to rigid body rotation and doesn't contribute to deformation at all. Right? So he said the stress has to be entirely determined only by the symmetric part of the velocity gradient tensor, and that is the deformation tensor. So this is the most important result in this part. But now we look at omega, we can further work on that. 5 minutes or so we have. So omega here is a tensor. It corresponds to effectively the action due to just the motion of a rigid body. Right? So now when you look at rigid body rotation independently, without any reference to the fluid, let's say an actual solid body rotating, that's what typically considered in rigid body rotation. Rigid body rotation, there are two important variables. One is the axis of rotation that we call as E omega, because the body is rotating about a certain axis. Now I can define a direction for that axis and I call it the unit vector E omega, and also a scalar omega, which is often referred to as the angular speed. That is the rate at which any element in the body is rotating, how much its angle changes with time, the instantaneous rate of change of angle. That's why it's called as the angular speed. Now we may define the angular velocity vector as the angular speed times the unit vector corresponding to the axis of rotation, right? So now, how many elements does this vector have? There's 3 elements: omega 1, omega 2, omega 3. Now we have seen, so what is the relation to an anti-symmetric tensor now as contributing to rigid body plane? Because we have seen that that is a net effect of omega. The omega now here we are considering as a tensor, right? So we know that, so we can talk of an angular velocity scalar, which is angular speed, right? Or the angular velocity vector, which is given by omega times q omega. We have also seen the notion of an anti-symmetric tensor representing a rigid body rotation. Now, because there are 3 elements to the angular velocity vector, because there are only 3 independent elements in an anti-symmetric tensor, we may also think of an anti-symmetric tensor representing the rigid body rotation. That is defined in the following way. So I have to define the 3 elements. This is somewhat arbitrary. Which one I choose is omega 1, which one I choose is omega 2, and which one I choose omega 3. But clearly the diagonal elements will be 0. That is for sure. You should not for the moment confuse this omega with that. This corresponds to a particular omega of the velocity gradient tensor. There I am considering the same notation is used typically in all those. When I am considering any rigid body rotation, it has 3 aspects to it. One is scalar, a vector, and then a tensor. So this is the omega 1, 2 element that is often, and there are different ways of defining it. So I'll just choose the one that I have here. Of course, I can call this also minus omega 3. So the omega 1, 2, we choose the third component, so it is easy to write down. Once I have chosen this to be omega 3, this can only be minus omega 3. And once I have chosen this to be minus omega 2, this can only be omega 2. So I still have a choice whether I can call this omega 1 or minus omega 1. I call this omega 1, this then has to be. This is the anti-symmetric tensor corresponding to rigid body rotation. Now when we write like this, the arbitrary ij element can be represented in this compact form as follows. Right? Epsilon ij k, omega k will give the ij element. I will ask you to let you verify. So if I put I equal to 1, j equal to 1, you should get 0. If I put I equal to 1, j, I equal to 2, j equal to 2, you should get 0, and so on to the diagonal elements. So off diagonal elements, you should get this matrix. This formula is consistent with this representation. Conversely, the kth component of the angular velocity vector can be written in this way. I don't expect you to remember these, but given these formula, you will be able to verify that they are consistent with this. Right? So clearly, this is not a thing which is dividing from here, because here there is a sum over k. Here I am referring to a k component, so this is actually a sum over I and j. The two are related, but not directly by just dividing one by the other. You may not get it. Right? So these are the two formulas. Now I can ask, given the omega here is given by this, half times whatever bj comma I minus bi comma j, or whatever written correctly here, right? What is the angular velocity vector corresponding to rigid body motion in a fluid? Because they typically, you start the notion of an axis very clear in solid body rotation. Axis is given and you're considering the rigid body rotating about with axis. So we have to also specify the speed of rotation. That is the angular speed. So those are very easily evident as parameters characterizing rigid body rotation. This I am constructing the tensor corresponding to the artificially and constructing this. However, here, to a different route, I find that an anti-symmetric tensor is the one that is characterizing the rigid body motion in a fluid. That is actually the anti-symmetric part of the velocity gradient tensor. Now I can pose the reverse question: what is the angular velocity corresponding to this rigid body motion in a fluid? You will find the striking result. Omega is actually the curve half times the curve of the velocity vector v. This gives rise to the whole notion of the concept of rotation in fluid is actually determined by the curve of the velocity vector. Because when we introduce the curve, it hadn't quite encountered any particular application where it appears. Now this is where it appears first, right? And we have the very well-known subfield called as irrotational flow, in which the curve of the velocity vector field is identically zero through the fluid. That will be called as irrotation flow. That's a very special flow. We consider those later. Right now, this you have to prove. You will certainly attempt to prove it, but we certainly prove it in the next class if necessary, and then move on to the rest of the Stokes' work. Are there any questions? Yes, quick question. Curve will involve a derivative. This is not that. Epsilon and k occurs in many different cases. We have to be aware of what is the significance where it appears. Here is simply a tool to represent the relation between the angular velocity tensor and angular velocity vector. So you can see the application of